welcome to the Certificate in Renewable Energies. This week, water, well, more specifically, hydro energy. Firstly, we're off to see a micro hydro scheme that's producing enough energy to power a family home. Now Wayne, we've heard of we've driven past the Clyde Dam and that sort of thing. This is in miniature. Can you explain for us, because it's a unique chance really to have a look inside a hydro unit. Can you explain to us what these parts are and what they do?
Right, well this is a micro hydro unit using a washing machine motor, a Fisher and Paykel motor. Basically what happens is the water comes down this pipeline here. On this occasion it comes from about half a kilometre up the hill through the bush, and it drives through a jet, a nozzle, which we have here, and this nozzle size varies depending on the pressure and that you've got running the turbine. And basically the turbine is made up of these little cups here, which are propelled to turn the turbine around as the water pressure hits them. They're quite critical how they're lined up. They've got to be lined up dead right to get the maximum efficiency from the turbine as it drives the generator.
And how do you actually do that? Ensure
well, basically there's a spot on here that we know we've got to aim the water at, and but in reality it's probably more a matter of putting a amp meter on the turbine and just tuning it to its maximum output, so you know you're in the right spot. And then there's a formula for working out, you know, what size nozzle and that you need at what pressure, water pressure you've got to get the optimum out of the turbine. And that's why it's not running today, is we're just getting rid of some airlocks in the pipe to get the maximum performance out of it.
Is it necessary that the inlet line is that long, or is it just because that's where the water source is?
Well, that's just on this occasion where the stream is, and the head of water is important too. This turbine has about a 50-metre head, so it's roughly the water's entering this pipeline approximately 50 metres above the turbine, and those factors are quite important as to the amount of energy you can get out of it, of course. So the higher the head, the more energy available at this end.
How popular are these units? You obviously have to have that stream handy, but are there many people taking up the option?
Well, it's not sort of widely used yet, but I think as energy prices rise, especially for the farming community, where we're going to see a lot higher line charges, and also into new areas, we're going to find more and more micro hydro projects going in. As long as the people have got water, well, they can be generating 24 hours a day, and it's pretty much weather doesn't make a lot of difference. Most people would generate 365 days of the year, 24 hours a day. So when you combine this with a storage system of a battery bank, and you invert it to 240 volts alternating power, where you can run normal appliances and that sort of thing, but usually pays to try and choose the appliances that are energy efficient, so you're not wasting the energy you've gained.
Now we know with the larger schemes there's of course a lot of resource consent involved. What about something domestic like this?
Well, there can be, depending on the size. If you're putting in a larger scheme, then you do need to go for resource consents and that, but for very small micro hydro, it doesn't appear to be a problem. The water's got to be returned back into the stream.
This is what this hose is?
Yeah, that just returns the water back into the stream. So you're not taking all the water out of the stream, just taking a very small amount of water.
And what sort of maintenance? Obviously things are moving pretty fast in here. Does it require regular attention?
It's like when you got a hydro scheme of any sort, there will be some maintenance required, you know, just keeping it tuned, making sure the owner will need to make sure that he's getting you know, the best output out of the unit. But generally the turbine itself and the generator should be pretty maintenance free, although there'll be a bit of work in just making sure, the batteries and so forth. A lot of that's all electronically done, but still, with any hydro scheme, it does require someone to keep an eye on it. There's quite a lot of fail-safe devices built into this because the batteries used here are very expensive, and when they reach their peak charge, the energy from the turbine now is dumped to the hot water cylinder, so the water is heated up when the batteries are topped up. And we need a safety device on that too, so that if the element fails, it won't damage the batteries because they're very expensive.
So you're always going to be getting the same, if you design your pipe right, it's the right part of the creek, you're going to get the same flow all the time, or does it vary?
Well, you should get the same flow all the time, but there's obviously filters up there to stop timber and particles coming down, and then also the main inlet on this particular one is just off the main stream, so that if the water floods down, hopefully it won't stop the water flow to the turbine.
And you mentioned the batteries. How expensive are these sorts of batteries, and is there a period of time where they are paying for themselves off, if you like?
Well, yeah, there's two schools of thought on the batteries, whether you use just cheaper lead-acid batteries and replace them more often, or you go to a more expensive battery and try and maintain them well with your electronic controls and that, whereby you get much longer life out of them, maybe 3, 4, 5 times the life of a lead-acid battery. But once again, the capital cost is, where you've got to pay the money to get the longer life. Some people maintain that you're better off to stick to just the cheap batteries, because if you do have a failure in some of your electronics, if you haven't got it done correctly, you can be up for a big capital expense. And that's why it's important in this house that at the moment it's feeding into the water heater to dump any energy from the turbine, but we will be putting another device on this that will stop the turbine if the water heater element fails, because that will eventually happen, and I wouldn't like the owner to ring me and say the batteries don't work anymore.
So that would just be a governor that stops the turbine, the water would still flow through?
The turbine will still spin,
but not generate.
It won't generate. We just have to have a little electronic control on there just to say when the voltage rises beyond the safety margin that it shuts the turbine down and probably brings a warning light on.
What sort of batteries and in what numbers does this scheme require?
It depends pretty much on the house. With a micro hydro, you can get away with about half the batteries that a normal house would have, because you've got this constant 24-hour supply coming in. If you had solar or wind, you'd need about double the amount of batteries of what this house has got, because you can't rely on sun and wind all the time, whereas this is pretty much constant 365 days of the year.
Well, Wayne, thanks for your time. I'm empowered, if you like, and would love to buy a place with a stream so I can put one in myself. Thanks a lot. Well, we're going to look at all three sizes of hydro schemes this show: small, medium and large. Let's have a look at medium. Well, Murray, here we are on the banks of the Mataura River. Tell us briefly the history of hydro energy and Alliance's use of it here.
Hydro energy has been used ever since the works have started. Probably back in 1878 when it started, there was some form of hydro generation. And it's a good way of making electricity for virtually no outlay and on a continuous basis.
And in fact, you were saying off camera that they powered Mataura's lights with the early schemes.
Yes, when it first started, it was originally put in for the freezing capacity to drive the compressors to freeze the meat, and it was belt driven back in those early days, but the excess capacity went into the town and it was used for lighting.
Now, how much now does this hydro scheme contribute to the overall energy requirements of the plant?
About 10%, and it's mainly used to take the maximum demand off the plant, but it's certainly a good way of reducing your power bill.
We had a wee look, and at the moment it's probably about 515 or something kilowatts. That's fairly good, isn't it?
Yeah, it is, especially in the conditions as we see the river today. It's excellent, really.
Yeah, the river today, it has been very dry this summer. How does that affect your generating potential?
Yeah, it does affect it quite a bit because we've got strict consents to work to, and probably one of the biggest consents is that we've got to keep water over the weir at 50 millimetres. And that's written into the consents, and without that, they wouldn't let us generate.
Firstly, what's a weir, and why do you have to keep that 50 mils of water over the top of it?
The weir is as we see, it's up the top of the river, and basically it enables the fish ladders to keep full and let the fish go up the river. So the council's deemed that 50 millimetres is what we require.
And we've seen some fairly good sized fish just walking around here.
Yeah, we have. And we're very lucky, like this river has got a lot of good fish in it, and as we were saying before, one of the other big things that come up this river is the cunnies. And it's one of the few rivers they come up, and they're still coming up, which is a good sign.
Now, I didn't know what they were till you told me. What are you talking about?
Cunnies are a lamprey, and they're a native type of fish and very peculiar to the Mataura River. And for years and years they've been captured in the river, and they still come up today, which is good.
So they've got eels with big suckers.
Yeah, they have big suckers.
And so how do they actually get in and interfere with the workings of the hydro scheme?
No, they don't really. They tend to try and head up the river and to spawn, and they mainly travel at night. So in the mornings, generally they're all gone. They stick onto the walls.
Now, behind us is I guess, where you collect the water. What are some of the problems that you've encountered with keeping that race clear?
We have quite a few logs that come down and when the river floods, but probably one of the things that we've faced at the moment is a lot of the gravel that's coming down the river because the council won't let gravel extraction continue. And we've just cleaned our race out here at quite a large cost, and I would say within a couple of years it'll be full again. And it affects our generation. We've probably lost 50 to 75 kilowatts an hour of generation due to gravel ingress.
And that must be quite annoying for you, overseeing this whole operation.
Well, it is when you're trying to run a plant and you've got to shut the race down. It does interfere with production, and there's all the associated costs with clearing it out.
What sort of maintenance is there ongoing with the race and then right into the turbine itself?
Obviously the race we've talked about getting the gravel out, and like just as a rough cost, it probably cost us $50,000 to clean that race out. And then when you look at the maintenance of the turbine, it's not too bad, like just a wee bit on the gearbox, but overall it looks after itself.
So it's very much a set and forget operation?
Yes, it is, yes.
Now, ongoing into the future, do you think that it will be viable, or will this problem with gravel make it unviable for you to use this water?
Well, it's something that we need to discuss with council, and hopefully we may be able to get a special permit to take the gravel out upstream so that it doesn't affect us as much.
We've been in the heart of the Manapouri Power Scheme. On what scale? How does this compare?
Very small on scale, but ideal for what we're trying to do, and to do our bit for renewable energy.
And that's an important part of the Alliance as well. Do you think there's potential for more, perhaps solar here?
Well, I think there is potential for more. The way the climate change is and carbon tax, it's going to come into its own. It's one of the big things nowadays, and we've really got to get on board with it. Energy is going to be one of the biggest things in the future for companies like Alliance.
How much of the river do you think you take? It's a small diversion, isn't it? And then it all goes straight back?
Yeah, very small. We'd be lucky if we took 10%, but again, in saying that, it depends totally on how much is flowing down at any one day.
Okay, now we know how much power it generates. Do you actually get the opportunity to return surplus power to the national grid?
We use it all, because even in our so-called off-season, the plant has great needs, and there's been a lot of changes, especially in the southern area with land use going to dairying, and what it's meant for the Mataura plant is that we do bobby calves in the so-called off-season now, and even last year we did a winter kill beef, and we hopefully will extend that, so any extra power that's produced is getting used.
And so that's obviously just going to get more and more, isn't it, as the plant gets busier? It's a 24/7 operation now.
It's 5 days a week, round the clock, and it certainly keeps us busy enough.
Well, Murray, thanks for sharing this with us today.
We're heading up the beautiful west arm of Lake Manapouri, heading towards that modern marvel of engineering that is the Manapouri Hydro Power Station. And yes, appropriately, it is raining, so we get to track the humble drop of water as it's converted to energy for our lives. Well, here we are deep in Middle Earth with Don Twiddle from Meridian Energy. Now, John, just how deep are we in Middle Earth?
Well, we're running about 180 metres below lake level. The lake sits about 178, and we're just a little bit above sea level at the moment. Depending on where you are in the power station, we actually go down to about 6 metres below sea level at the bottom extremity of the station.
Now, quite amazing, the whole feat. We'll get into the process of generating electricity, but to actually build this station was quite a feat for the time, wasn't it?
Yeah, well, it was. It was first conceived back in about 1904 by the surveyors who were running their tapes and measures all over the Fiordland, and for them to come up with the concept alone in those days was pretty awesome. It took a little while before they were actually able to turn that into a doable engineering project, which happened with discussions with the aluminium smelter in the late 50s, and came through to actually turning the rubber onto the road in the mid 60s or early 60s, commissioning in 2 stages as the machines become available through to about 71. The first machine, the last of the machines was generating.
So here we are, we were on the surface of the lake in the rain on our way in here on the boat. Quite amazing to think that a drop of rain ends up producing power at the other end. Without getting too complicated, describe the process.
Okay, well we run on water, and rain is good for us. That's why we're here. That's why Fiordland's here, and Fiordland processes water very well. And we have very high rainfall. We take that water that's accumulated in the lakes, that comes from the headwaters and the catchments of Lakes Manapouri and Te Anau. They both feed into the same lake. And we capture that water, and instead of the water going south down the lower Waiau to Waiwai Bay, the majority of it now, aside from minimal flows, the majority of it goes through this power station and out to Deep Cove, about 10 kilometres away. So the energy in the water is basically derived from the natural level of the lake with respect to the sea level. And that 178 metres, depending on lake level, depending on tide, etc., is the potential for the energy that we use. We use that water up to a maximum of 510 cumecs to generate power through these machines. That's the motive power for making the turbine runners turn and to make the rotors turn and to stimulate the stators and to produce electricity.
So we've got an inlet up top
That's
feeding
correct.
these machines. What are these machines and how do they work?
These machines are rated at 135 megawatts and they rotate at 250 revs per minute. Water comes down out of the lakes in 7 individual penstocks, and it enters a spiral like a snail shell shape and is forced into a rotation flow, which applied through wicket gates and control gates onto the turbine runner, which causes the turbine runner to rotate. That turbine runner is attached to a shaft, which in turn causes the rotor to rotate inside the stator of the main generator. And the generator itself generates 13,800 volts, which in turn is transformed through the unit transformers to 220,000 volts, or in our case slightly higher than that because of where we are with respect to the rest of the country. We tend to generate on the underside of 230,000 volts.
Just for people at home, what voltage when we plug in our hairdryer and that sort of thing, what voltage have we got at the wall?
Okay, at the wall you're looking at 230 volts, and we are generating 230,000 volts. Well, we're not generating that, we're transforming to that for transmission around the country. The nominal transmission voltage is 220. We generate a little higher than that because of where we are. And that goes up 7 dedicated cable shafts to the switch yard above, which is really the only other thing you see when you come in on the boat. Our footprint here is very small. You don't actually see the power station.
It is amazing, isn't it, to think that it was constructed in the 50s and 60s, still with that mind to the environment even then, and it does the minimal scarring. There is no damage really to the environment here.
Agreed. But that said, there was a bit of a cavalier attitude out there, and there was a plan to raise Manapouri 100 odd feet in those days, 30 something metres, which would have joined this lake with Te Anau, create basically one big super lake. That was going to be a structure downstream of where the Mataura comes in, and thankfully that didn't happen. The protesting through the Save Manapouri campaign resulted in the ousting of a government and the creation of a new government who gave undertakings to actually take notice of that protest movement. That formed the Guardians of the Lakes, and in fact probably fundamentally formed a lot of our environmental guardianship, I suppose, around the country. A good outcome, definitely a good outcome.
Quite incredible really to be using that rain and turning it into energy to power our lives.
Yes, it is, and it is a renewable source, and Meridian Energy is very much in sustainability and renewables. And for us, we're using what naturally occurs, and we're using it very responsibly and in a caring sort of a way. And we maintain the levels of our lakes and the levels and rates of rise and fall of our rivers to natural guidelines.
Recently, there's been quite an overhaul. What work was actually carried out?
Well, recently this was the half-life project, which is basically the half-life of our machines. We have a life of our machines 50-60 years type of thing. Halfway through that period, our machines are starting to get a little less reliable. They're certainly not up with the technology of the day, the current day. They were good in their day. We couple that with the previous large project here, which was the second Tailrace tunnel, which gave us an ability to extract more electricity from the same amount of water, equivalent to about 64,000 homes, really for no cost to the environment, and also another ability of us to physically generate more should we wish to, and at times we do wish to. So we had to match our machines to that. So they've actually been increased to the current 135 from 105. That includes the machines, the cabling, the transformers, and pretty much the controls, everything got bolted on. The principles haven't changed, the principles are very similar, but the stuff that controls it is very sophisticated and it's state of the art. There's the largest brushless exciters in the world.
There was some fairly sophisticated machinery employed to dig the second Tailrace. What about the first one?
Very dangerous, very dangerous. The second Tailrace tunnel was built with a TBM, a tunnel boring machine, special machine constructed for hard rocks. And if you like, a lot of the interface with the rock, with the mountain, was remote because the machines were built to do the work and the guy just operated it, and there's all the ancillary equipment. The first tunnel and the first construction of everything underground here involved drill and blast, which is the old-fashioned method of a drill into the rock, pulling the drill out, putting dynamite in there, plugging it up, hooking it up with detonators and then setting it off. Very manual process, very dangerous process. That, along with the machinery, the big muckers and electric locos and whatnot that were travelling up and down the tunnel, made for a very dangerous environment. In fact, we lost 16 men building this power station initially, the power station in the tunnel. Another one was killed on the pass going over Doubtful Sound. So yeah, an extremely high cost in lives. This current latest activity of the new tunnel, no lives lost. Excellent outcome.
Okay, so also it's not only a powerful generator, but it's also a feature. You're getting tourists, as we've just seen up on the viewing deck there. How many come through a year?
Yeah, 40,000 these days, and that looks to be going up and up until it probably hits some sort of a Department of Conservation limit of amount of people in the area. But yeah, we have people who are able to come into the visitor platform. They don't go down on the machine hall like we are here because of OSH and the like. But they have pretty good access, to be honest, and we often get comments from overseas visitors saying how that you just would not get this opportunity anywhere else. Little old us, you know, we're affected by things like 9/11 and whatnot, so we do have to keep a close eye on how things like that are progressing. But at the current time, yeah, it's great if we can showcase our station. We're very proud of it, very proud of what we do here. If we can showcase that to the world, that's good.
So you're effectively, for the layman, using a mountain as a dam really between two volumes of water.
Correct, because the natural head was there from Lake Manapouri to the sea, except that the outflow was typically down through a southern reaching river, and now we've stopped that outflow or reduced it to a minimum flow of around 16 cubics, so that river stays alive, and the majority of it now goes in a westerly direction. And so that natural difference in head was there, and all we did was tap into the underside of it really and put a power station along the way. Very simple.
Now, Meridian's obviously very conscious of the environmental factors and that sort of thing, and sustainable energy. Is there potential for even more energy as time goes on out of the station?
Yes, there is. We are constrained currently by resource consent. We have a limit on how much fresh water we're allowed to put into Deep Cove, and that sits at 510 cubics, 510 cubic metres, 510 tonnes per second of water to Deep Cove, which is a substantial amount of water. And we are looking now at whether or not we can up that, because we can certainly physically do it. Whether or not it's a good thing for the environment is what the scientists are getting their heads around now, and we're talking to people about that. So physically we can go up, and we have got up to 907, and that was with permission from all the stakeholders back in July last year, to just run a high flow trial and see what the outcome would look like on the surface of the water, see what it would look like to currents in the Deep Cove, etc. And that's all in the interest of getting the science right. So yeah, physically we can go considerably higher. I don't know whether we would physically be able to do anything additional to the power station. I don't see that you could build this power station now in the current situation of being a World Heritage Area or a national park, but we can certainly do better with what we've got and be very efficient with what we've got. That's the thrust.
Okay, so how many houses are you powering with this station?
For this station, obviously couldn't tell you how many houses, but it's equivalent to a little over 4,000 D9 bulldozers. So if you think of it that way, that's probably something you can get your head around, if you can imagine 4,000 D9 bulldozers.
Sounds interesting. Well, thanks, John, for enlightening us on hydro energy.
Very welcome.
Cheers.
Very welcome.
Thanks for watching this week's Certificate in Renewable Energy. If this course interests you, or any other for that matter, then please phone 0800 SIT to learn for more information. We'll see you next time.
Heading up the beautiful west arm of Lake Manapouri, heading towards what is that modern engineering marvel, the Manapouri Hydro Power Plant. And we get to be interrupted by the guy talking.